Cool, so we have it here, then let's do code and traversing the linked list. So we have our linked list here. Is that big enough in the back? Cool. And this linked list node is, we have 555, 556, 41, 33, 150, and 11. So if that will be sort of the order. And this is, we're building this list manually by manually connecting the nodes, saying in 1.next is equal to n2 and so forth. So here, let's do this then, and let's see. So we do, let's call it const current node equal to the node, and then while we have a current node, let's console.log the current node, and let's do current node equal, sort of moving the pointer. This is sort of like, this will be the equivalent of I++ in a for loop, basically, right? Dot next. So let's try it out. Let me close this here. Let's open the terminal down here. I wonder if we could put, yeah. It's node 1, traverse, the linked list. Oops. Here, first of all, we want to console log the current node value. And when we have an assignment to a constant variable, which is const, we need to change that to let. And we get undefined, undefined, undefined. Okay. That's some progress. We got at least the same number of console logs, hopefully. And we have one less, I guess. 5. Is not that value? Val. Cool, did we get that? Yes, we got the same thing. So, questions about this one? Yes.
Was there a preferred way of doing it, or just?
No. Yeah, the recursive way is also cool. Let's see that one. Const traverse recursive node. And just with recursion always has these 3 laws that I was reading about here. I knew them, but I didn't have like more accurate language to it. The 3 laws of recursion are every recursive algorithm must have a base case, which is sort of when the recursion stops. It must also change its state and move toward the base case. The last one, it must call itself recursively. And this one is sort of, I would say this one is the trickier to find. Like, how do we change the state to move toward the base case? And sometimes figuring out the base case is also a little bit tricky, but let's keep these 3 pieces in mind. So also, I like what is said here. Yeah, a base case is typically a problem that is small enough to solve directly, right? So base cases in general, recursion are small cases that we can solve directly. So what is the smallest input we could get here on the node? Null, that's 1. So let's check for that. If not node, what do we want to do? Do we want to console log anything? Just return, right? Okay. So if we have a node, then what do we want to do? Let's say, so the first input is when we get a node that is null. So that's not a null, it's not a node at all, it's just null. Basically like an empty linked list. And the second example is we get this node with value 1. What do we want to do if we get a node with value 1? Let's say our linked list is just one node. What do we want to do with that node?
Print it.
Right, console log it. Node value. Okay, so just with this, then we have our base case, and if we pass in the last node, it should work. Let's pass N4. Let's pass N4. Wonder if I could do N4 is our last node. Let's try it, see if it works. Wait, do we have traverse recursive? Well, is N4 our last node? No, our last node is N5. So we get undefined. Spelling mistakes. Cool, so it works for one node. Let's try if it works for two nodes. Doesn't work for two nodes. So this is, I have my base case, but I'm missing the recursive step, which is calling itself, as well as the means to move toward the base case. Also, I think I'll share this article later on. I think this also said reducing. No. What was the other keyword that I remember? Yes. Yeah, let's read this. To obey the second law, which is we need to have a change in the state to move forward, to move toward the base case, we must arrange for the change of state that moves the algorithm toward the base case, right? A change of state means that some data that the algorithm is using is modified. Usually the data that represents our problem gets smaller in some way. This is also common. Like your data will get smaller. So what we need to do in this case is make the list smaller. Because we know how to print for one node. What if we could use sort of that for the recursion? So in here, then let's just call the same function. Now let's make our list smaller in a way. What could we do here? What happens if we pass a node? There is your favorite website, or our favorite website, it's mine as well. The Stack Overflow. So in this case, our recursion stack just filled and it overflowed, and we got this error: maximum call stack size exceeded, because right now we have our recursive step, so we have a base case and a recursive step, but we don't have that means to get towards the base case, and we never reach that base case. Therefore, we get an not infinite loop. We get a stack overflow. So let's just pass in here next. Let's pass in the next node to the list, and let's try this out. Oh, so that worked for N4. Let's pass it N1, and we have our list working. Let's pass in null. And we have our print traverse recursive working. Note that, like, even if I pass in N3, N3 is a node in the list. Our algorithm sort of just picks from there, right? And these two are fine ways to traverse a linked list. Questions about the recursive approach? What do you think will happen if we console log? So let's look at this. Oops. So we console log in here, and we get the order in the same order: 256, 41, 33, and 150. What happens if we console log here? Would anything change? Let's see how it changes. That's really weird. We sort of reverse the linked list. let's console log them both ways. So sort of starting at the beginning and then in the end, it does that, right? Any suggestions for what this might be? I mean,
because of the stack,
because of the stack, because of the way in which our recursion is working, right? We are console logging before. Let's see if we can do it here. So we have a stack, and we have our linked list, which is, let's see, 6, 41, 33. And 11 is the last one. So we have this linked list. Now, the way in which we're doing it is our recursion will start on this node, right? And then once we have that, we just console log it. So let's think about first sort of this one. Before our recursion starts, we just console log 556. Then what happens is the recursion starts to recurse by calling our function that I'm just going to call tr. And now the root node that we passed was the next one, right? So I'm just going to draw it here for the representation with 41, right? And then when we call tr, which is traverse recursive, and we pass in the next node after the first one, we pass that 41 and we get 41 printed in here, right? This is our console log as we're sort of going right now. But the recursive traversal of this linked list or this node hasn't finished yet. This one will call the next one, which is going to be tr on the next node, which is the node 33. And this is what we call the node. This is the input to our function that I'm just representing here, more readable. So we get 33. Then 33, we print that one, and then we call. Same with 150. We're at node 150. We print that 150. tr with 11. We print that 11. It turns out that we actually call our recursive function with null, which is the next one of this one. And this is our stack. This is literally how it is like internally. Now we call that with null. What happens when we call our function with null? It just returns. When a function returns, it's popped off the stack. So what happens is that one gets popped off the stack, right? And now let's go. So that was popped off the stack. Now let's put back this second console log. This second console log will run after the call gets popped out of the stack, right? Because let's say we call tr in 11, then we saw the 11 printed, then we call it with null, that finish, that pop that call from the stack, but tr11 hadn't finished. Like the recursive call that tr11 made, which was tr with null, that one finished. But tr11 didn't finish because there's still one line to run, which is the second console log. Now that one executes, and then we get console log in the sort of the other order, which is we get 11. Then the recursive call and then this one gets fully popped off the stack. All right, like a function gets popped off the stack when it returns, or when all its statements have been executed. Right? Now the recursive call that TR with 150 had initiated, that was finished. Now it just popped, right? And then TR of 150 hasn't finished because we still have that console log. Then 150 gets console logged. That one is done. The recursive call that TR of node 33 had finished, and then the same thing just repeats, and we get this sort of in this other order. And then the call stack is being popped at every step, and at some point we go back to having just an empty call stack. So this is the way that I like to imagine is, I haven't found more accurate sort of language to describe it, but it's like, I like to imagine it sort of like the recursion going down, but at some point it has to come back up. Or you might imagine it the other way around, which is going up and then it has to come back down. Like the stack literally goes up first, and then it has to come back down. If it never comes back, what do you get? If we just keep filling out the stack overflow, right? Cool. So then this one is that one. Final questions about this one. Okay. How did this one go? Thumbs up if it went well. Okay. Anyone wants to describe the approach? Owen.
Start off with an empty object and empty array.
Where did I put my marker?
It would be like an array that we get from functions. And it would be and if we like a key didn't exist, like in the array, like a number, then I would create it. And then I'd set underneath the value to 0, and I'd add like 1 to the value.
Got it.
And then if it didn't, if it did exist, now we add another thing to the value.
Yep, that's the right approach. So the first question is like linked list. You have to be familiar with linked list. This question is, are you able to use a hash table or an object to improve your runtime complexity, basically? Now this one, like the first approach you might think about it is just like we could have two nested loops to keep count. We will also need an empty array to check whenever an element surpasses or is equal to that count, we just add it, and we know that then the time complexity of that will be L of n squared, right? It will be two nested loops checking each time. So the approach that Owen is suggesting is, what happens if we have an object? I'm going to call this one object maybe just tracker. And we start with an empty object, and then we have our array. What was the array we gave was, I'm just going to do 1, 2, 4. Three, 4, 3, 1, 2. So we have our array, and then
The second two was a 3. The first two was a 3.
oh, thank you. We have our array, and then the idea is, what are hash maps good for? Constant time lookup, right? By key. What else are they good for besides that? Yeah, what are hash maps good for? Fast lookup.
And also fast insert.
Fast insert, that's correct. Others?
Holding metadata?
Yes, but not what I'm looking for. Owen.
Comparing values.
That'll be the same as fast lookup. Can we have repeated values in an object? Right. So objects are good, and hash tables are good for uniqueness as well. Well, actually, I shouldn't say like since we have our hash tables are objects, and then we have objects have properties which are key value pairs. The right way that I should say is like, can we have duplicate keys in an object? We can't, right? So objects are good for fast lookup and keeping things unique. Can you repeat the approach?
Yeah, so I had an empty like tracker, empty object.
Right.
And then I had like an empty array.
All right, we have an array. Let's call that one like output. So we're gonna fill it out. I'm just gonna draw it like that, empty.
And then like the function, we have an empty array and then the number of times, like the array and n. So I looked
Right.
at, I looked at the array that was given.
Mm-hmm. Okay, so you're looking over this array.
Yeah.
Got it.
And if like the number in like the element doesn't match anything in my tracker, then I add a key.
Okay.
That's equals like the number.
So you're looking, let's say, with I, and then I is 0, and then the current element is 1, and then you're checking. How do you check if it's in the object?
With if statement.
Okay. So tell me what that if statement looks like.
If the if the tracker bracket array .I, it doesn't exist. So I put like
Oh, if it doesn't exist here,
yeah,
like negating the conditional.
yeah.
So
Exists and set the object or tracker array I equal to 0.
constructed the key array I. Equal to 0. Okay.
And under that I put the same thing, plus plus.
So do you have an else, right?
Yeah, that else under.
Right. So let's do that here. We have else. We have this literally the same thing with his tracker. That current element. Plus plus. Or plus equal 1. Oh yes, thank you. Yes, this is 1. So we are sort of keeping our object is sort of keeping us count like tally basically, where you keep track of how many things you have seen so far. So this approach is like the most efficient way to approach this, where you basically you're standing in 1, you check if that's in the object. If it's not in the object, you just initialize it with 1, and we set the value to be 1. Like on the first time, this is gonna give us false. Wait, is this gonna give us false or true on the first one? First time is true, right? Because this is checking. This is again using sort of the truthy and falsy things, where when you look at a key in an object, at least in JavaScript, and that key doesn't exist, what do you get? When you look at a key in an object and that key doesn't exist in JavaScript, what do you get? Undefined. You get undefined. In other languages, it breaks. In JavaScript, you get undefined, and undefined is a false value. So basically, on the first try, we're trying to check if 1 is a key in this object. 1 is not a key in that object. We get undefined. Undefined is falsy, but we then negate that, and we say, okay, this is another way of saying this is if that key doesn't exist, then let's add it. How do we add a key in JavaScript to an object? You just key into it, right? Now, this is just in case that you don't remember what it, or anyone remembers the exact name for this syntax of keying into an object. bracket notation, yes. Other words for that, same thing. So we had like the dot notation, right? We got bracket notation. This one is also known as computed property. What that means is when you have your key inside of a variable, like in this case we have our key is inside of array of 1, we need to use square bracket notation because the key, we don't know the key. Like the key will be one of these numbers. So this is known also as computed property notation. So cool. So if it's not there, let's initialize it to 1. So we were here, 1 was not there, then we move on to here. Is 3 there? No, so let's just add it, let's initialize it. 1. We move here, is 4 here? No. Let's initialize that to 1. We move here, is 1 in the object. Right? So then this doesn't return true anymore. This if condition doesn't return true. We fall in the else, which says just increase that number at that key, which is 1 in that case. What that ends up doing is that increases that 1 to 2. Is 9 in the object? No, let's initialize it. Is 1 in the object? Yes, again. Then we don't fall into the if statement, we go into the else because that key already exists. And we just increase this number to 3. Then we see 3. Have we seen a 3 before? Yes. So let's just increase the count here. Oops, that was a jump. So we were here, 3. We get 4. 4 we have seen already. We just increase that. 3, one more time. We have seen 3. This one goes up to 3. From 2 to 3. 1. This one goes up from 3 to 4 now. And then another 2. Oh, this is the first 2 we see. That one doesn't exist in the object, we initialize it. And then at the end, we end up with this object, which is literally a tally of a count, with the count of the elements. Right? Then what do we do from here, Roy?
That first thing is the whole thing is a for loop, and I made a second for loop to the object.
Mm-hmm.
So basically, it was like I did a for loop to look for element in object. If the object bracket element is less than or equal to n, then push the element filter red or just a red output.
Right. So once we have here, we can loop over a hash table. One thing to keep in mind is, like, again, this is another one of those scenarios where it's always a trade-off. Like, we get a hash table, and it's really fast at lookup, it's really good at keeping unique values, but doesn't guarantee order. Where when we loop over an object, we don't know what order the keys are going to be visited. We can loop over them, but we don't know in what order they're going to come. Yes?
I skipped the loop instead of interesting at the end of like a separate.
Oh, like here. Yeah, that's good. Let's do that other loop, and then we see like how we actually don't need that. Right. So we're just gonna loop over the properties of this object, checking each one to see if the value is greater than n, is greater or equal to n. If it is, then just add that to our output. So similarly, we're doing that. So we let's say for some reason we go first into the for because again objects don't have guaranteed order. So we go here and we land on key 4. Is this one greater or equal to n? No. So let's say we just move on to here. Is this one greater or equal to n? No. Let's just move here. Is this one greater or equal to n? Yes. Let's put that onto our output array. Then let's say we move here. Is this one less? Did we already visit this one? No. Is this one greater or equal to n? No. And then lastly, let's visit this one. This one less or equal to n. Greater or equal to n, we got n1. as our value. So questions about the approach. Okay, let's do that one. Let's close this here. Let's say anyone has another name for the object as maybe more intuitive? Occurrences. Okay. Let's do const. So we start an empty object, then we're gonna loop. Do we need the index? Oh, yeah, let's do it with the index. So let's do for let I equals 0 while I is less than the array.length. Then I plus plus. And I don't want to type that amount of square brackets, so I'm just gonna set here something like let current equal array at index I. And then we're gonna check if the current element is a key in our object, saying if occurrences has this number, or if it doesn't have this number, right? So let's negate this. We could do that, or we could also do triple equal undefined. This is a little bit more elegant and expressive, saying if it's not there, then let's set occurrences, the current element equal to 1, else let's do occurrences plus equal 1 or just plus plus. Cool, so let's just do this and let's have a console log here. Console log occurrences. Let's see if we actually get the same picture that we got here. Oops, I'm still running the alt 1. 2. Cool, so we get 1, 4, 2, 1. So you see, like, this is what I was saying about the order. You see here, I made these keys in the order as I was visiting them on the array, but when I console log it here, it comes in a different order. You see the first one, the third. Oh, I wonder if internally maybe it does some sorting and arrange them in some order, but that doesn't really matter. We get that the key 1 has a count of 4. That matches what we have. The key 2 has a match of 1. The key 3 has a count of 3. 4 has a count of 2. Wait, did I skip 4? Oh yeah, there it is. And then 9 has a count of 1. Right? Yes?
So if you add a 0 to the array but not show an object?
Say that again. Like if we have a key.
The number 0 to the array but it not show an object?
That's a good question. Let's try it out. Let's do 0, 0. It shows up there with 2. Oh, what's this? Undefined. Oh, I left a blank. Thank you. Well, even undefined got hash. Yeah, so that will still do. Also, it's important to note here that like when we talked about hash tables and we talked about the key ends up being a string. So you can see that our array has numbers, but once those get converted into the keys of the object, they become strings. Right? Cool. Questions so far? So this is a very common sort of pattern that you may use. Like another question I think I studied as a practice question is find the most common element in the array. It's literally the same question. Where once you made this, you just check which one is the largest count, and that will be the same. Or the opposite, find the least frequently found element in the array, right? And it's common to add stuff to an object for fast lookup, like in this case. So once we do this, then the other loop that Owen was describing is let's then loop over the keys of the objects with let's do for let say key in occurrences. Oh, but we also need like an output, so let's let output an empty object, and then we check if the occurrences at that key, maybe this should be called number. Let's call it num. That's what our keys are. If that occurrence, if the value of that key is greater or equal to n, then let's do out.push that number. And then here, just do return out. Right. Then let's console log out right before we return so that we just see it. Just to see it rather than anything else. Let's run this. Oops. Console is not a function. Cool, and we got our result, 1 and 3. Questions or comments? There's one slight problem here, which is these are not, 1 and 3 are the most frequent elements, but they are coming out as strings, where they should actually be numbers. Yes, Michael. But we could just use number here.
No, in the output, the push.
Oh, like here? Oh, right, we got that. Questions? Cool. So let's see how we wouldn't need this for loop, right? We got this other for loop, but what we could do is we could just check every time we increase a count. We just check if that one is greater or equal to what we're looking for. So in the end, Malik, where do you have the?
So it's after my else statement.
So let me put output all the way here at the top. Right here.
Yep. There's like a separate if statement that says if occurrences at current element
Mm-hmm.
is greater than or n.
And then
we do is we output that push, or whatever output that push current, so what the current element is.
oh, and then you save yourself of having to convert it to a number later on.
Wouldn't that then after
When there's like 3 of this one.
oh, sorry. I changed the value of the hash to push so that see how it went there 4 times, it doesn't push one into the output twice. Because if you don't do that, it's gonna push one to the output twice.
Oh, I see. So let's see this. Right, so we get this problem. Okay. How do we solve that?
I changed the value.
You change what? The value?
The value of occurrences that current to push, a string called push.
Wait, so you said you had something else around here.
Right, it's after line 22. So
What do I do here? Oh, okay.
Current equal push.
Equal push?
Yeah, string.
Oh, I see. Something like this? Okay.
What if,
Oh, but this is, yeah.
what if something appears 6 times?
Yeah, I think this is gonna give us a problem. Because if you change it, so let's add another one, and another 2 ones. Oh, I guess.
If I change it back to number, so if it appears like 6 times, 7 times, wouldn't it go back?
So you push this one. Where are they all? We're consolidating the.
2, divided to 1.
Right, where it should say more than that because we have all of this. Other ideas?
Add more ones.
Add more ones?
Oh, you mean like to solve that issue? Yeah,
Columns with 1, 2.
We get it back. Janesh.
So greater than equal to, just make it
Equal to 3? Oh, that's a good one. That's a kind of clever one. If we do equal to 3, the first time it's equal to 3, then it's going to add it. And when it's greater than, you already added it. Don't add that one. Wait.
Yeah, you gotta take out the first.
Right. We could do that. This is starting to feel a little bit uncomfortable. Something we could do. Yeah, no, I think we got the point across about the hash table approach, which was the core of this question. Well, any final thoughts on this one? Cool, let's move on. 3, sum stack. Thumbs up on this one if you managed to get this one. Also, maybe it's something that I should have specified. I hope you didn't use any array methods or you didn't do any loops that are looping over the array. Raise your hand if you have a for loop on this question. Well, if you have a for loop and you're doing index of something. You can have a for loop, but as long as you don't have, as long as you're not accessing this data array, if you're doing this data array anywhere in your code, in your function, then that's wrong. The thing with a stack is about sort of respecting the properties and the methods of the stack and following along those rules. So we have a stack. In this case, it's going to look like 14. 14 is all the way at the top because it's the last one that was pushed. Then 91 under there, 88, 267, 12, and 10. 10 is at the bottom of the stack because it was the first thing that was added, right? It doesn't really matter the fact that we sort of forget that it's implemented as an array and just think of the stack with its operations. And then our goal is we need to add up all the numbers in this stack. How can we do that? Yes?
I created 2 variables. One was sum, which is set to 0. The other was peaked num, so I could keep a record of it. And then I made a while loop. So while the stack I did not stack is empty, so that way I can make sure that the empty, so it's not gonna, it'll stop when it's empty. Peak num equals stack dot peak.
Cool, so let's do that.
Okay.
So you got a total variable? What do you call it, sum?
I just call it sum.
Okay, I'm not gonna collect sum because I call that the function.
Yeah.
So let's say total or result. And then you have something else called peaked element.
Or num in my case, but yeah.
Oh, okay, let's do num. And then what do you do here?
I made a while loop.
Oh, the while loop goes before num or after?
After. So num I actually just left empty. Like so it was
Like
sort
that?
of like let and then code
Okay, and then you have a while loop. And why are we while what?
So stack is empty. Or stack dot is empty. But I put a dot in front.
Okay. So while the stack is not empty, then what do we do?
So I set peak num to equal stack dot peak.
So we give num equal stack.
Oh, yes.
dot peak. Wait, peak like that. Okay.
And then it was results
Result
plus equals num.
plus equal num. Okay.
And then stack.pop.
And stack pop.
And then just after that while loop, I did a return num.
Return. Oh, in my case, result. Right.
Oh, that's right.
And then let's console log here. And let's try this one out. Node 3 sum stack 482. Questions on this one? Yes.
For stack, should we expect that when we pop them, it's going to return the value every time? Or should we do it like this where we set a
Yeah, we could actually get rid of the peak. Like we could just pop directly, right? We could just pop directly because pop returns the last element. So in fact, we could do this. Let's do pop here. And we can actually keep this variable local here. Say let num is, we remove the first one, and this should still work. So we look at we remove the first one, we save it into num, then we just add that one to our result. That will be 0 plus the first thing, which is 14. That our result now is 14, and so on. Yeah, so basically this is like a little bit, it might seem counterintuitive, but like if you have a stack and you need to look at every single element, you need to pop them all. Because that's the only way in which you can look at the stack. Like if you're asked, find the element in the stack, you need to take all of them out. Because there is no access to the index. It's not a hash table that lets you do lookup by key, and so on. Let's say here there was a constraint about, oh, okay, so sum all of them, but restore the stack. You have to leave the stack as it was. What do we do there? I mean?
When you pop them, you push them to a new stack, and then you go again over this stack and pop it, push it to the first one.
Mm-hmm. You everyone hear that? Yeah, we just put, when we're popping, we put it onto another stack. At the end, once we get our sum, we just make sure that we push everything back onto the previous stack, the original stack, right? Questions or comments on this? Could this one be recursive?
Yeah.
Right? Everything you could do recursively, you could do iteratively, and vice versa. Some are easier one way than the other way. Cool. Final questions on the stack. Okay, let's go to the queue range. Queue range is similar in the sense that we're gonna need to take everything out of the queue for this one. And this one is asking us to write a function range that takes in a queue of numbers and returns the range. There was one mistake here, which was the order of these words. There should be the difference between the maximum and the minimum. I don't know how to spell minimum. But the only difference is it's gonna give you a negative number if you do it the other way around. So a range is a mathematical term for like if you send out a survey, you want to know what's the range of the values you get. So you look at the lowest value and the highest value, and you take the difference, and that gives you the range of your survey results, right? So here, what we need to do is find the highest value, find the lowest value, and then subtract them, right? Any approaches for this? how do we find this? How do we find the highest value in a queue? Yes. We could pick. Okay, so do we pick all of them? Do we have to remove them? We can't really iterate, or through, we forget about the array that's under the hood. Is this an array under the hood? Yes.
Well, we don't care about the queue. You can keep peeking and queuing.
So keep peeking and dequeuing. Okay. Say
So
more about that.
While loop, and it's checking to see if the queue is empty, and I check if the current one I'm peeking at is less than the minimum,
Mm-hmm.
and if it is, I make a new minimum that peak, and the same with maximum, vice versa.
Mm-hmm.
So I two statements next to each other, and when that's done, I dequeue that one I was looking at and peek in the next one.
Right. So the approach is you keep two variables, one for max, one for min. Just like you would do it in an array if you're asked to find the highest value or the lowest value. You need to look at every single element and check if it's less than the minimum value you have seen so far. If it's less than the minimum value that you have seen so far, then that becomes the new minimum. And you also compare it to the maximum to see if it's greater than the maximum value you have seen so far. If it's greater than the maximum value, that now becomes your new maximum, right? So this will be something like this. Let's do let min. Should we start with any values? Let's do let max. And then the while loop is as long as there's stuff in the stack, right?
Yeah.
So as long as the
So it's not queue dot.
oh queue, right,
Isn't.
is empty. So as long as there is stuff in the queue, what do we want to do? We said
Compare if the minimum is greater than the first.
so. Let's do something like current. Should we peek or should we pop?
Well,
The queue.
I
I'm still in stacks.
But then what's the point of having a peek?
Peek is just in case you want to peek.
Yeah, well, you are peeking, but you're also comparing. Also,
Here,
equals.
that's a good option. Yeah, let's have this as a peek. So let's initialize this one as, we're going to say our minimum is going to be the first element, and our maximum is also going to be this first element. We could also start, I think I saw some of you starting at minus infinity and plus infinity. Those are also fine values. So we say current, and then,
I think you have to actually write out for
oh, thank you. Q, and then we just pop. We could just pop here, right? Thank you. DQ.
Can't really do that. I mean, well, I was just thinking, like, I want to check.
So we have current, and then we can just check that against the min and the max. On the first check is not gonna do anything because the first current is the same as the min and the max. But on the next one, then it's gonna work. So even though like we're doing an extra if check, that's not match. That's not gonna grow as the input size grows. Therefore, we don't care. We can consider that constant time. So we do current greater than the max. Then we say our max now is going to be our current. Else, well, we're going to need to check else if the current is less than the min, then let's have our min be our current. Do we need any other checks? Okay, so let's try this out. Then that's while the stack is not, while the queue is not empty. So let's console log here min and max, see if we find them. And then let's call that with our Q. Still calling the wrong one. So, okay, we got our mean being minus 145 and our max being 98. Right, this is our lowest number and this is our highest number. So we're able to find the highest and lowest numbers, right? And similar here, like why do you have to restore the queue? Because at the end of our program, the queue is empty. But you may, depending on the problem, they may ask you just make sure to restore it to leave it as it was. And then similar, we could just push into an array and then queue them all back in. Cool, and then the answer will be, yes, questions?
What if we had just two elements, both the same value?
That's a good question. If we have 1 and 1, what's the range between 1 and 1? Is that the right value?
1 minus 1.
Right.
Range between.
Thank you. I'm not sure if this is going to give us the answer. Let's just look at the. What is it like the math definition?
So if you go the website, Wolfram Alpha.
What's it called? Like the animal? This is like I just write it like this? Wow. This is 1?
Yeah.
Cool.
Yeah. That's the point in the.
So the range of 1 and 1 is 1.
Yeah.
Say that again? Let's just look at this. I don't know the answer. I don't know that much math.
Can you go down? That one?
Uh-huh.
Right side.
This one?
Yeah, so it's like this flat line and it'll be the.
Right, but then this is 1 and 1.
No, like the points go along the axis, so it'll be flat.
Here?
Yeah, so the function would be y equals 1. It would be a straight line across.
I see. Got it. So it's 0.
Yeah.
We have. Which one? This one?
Yeah.
Yeah, so the range, the range of 1 and 1 is 0 then. You got no range, right? That makes sense. If all your values are the same, you got no range. Cool. Any other questions about the queue? A queue, like, we might get to see this later on, but a queue, the best implementation, or a better implementation, I shouldn't say the best, the better implementation of a queue will be with a linked list. Why would it be better to have a queue with a linked list than with an array? Yes.
Because you always know what's behind it, like behind the elements.
No.
Okay.
Malik.
Because in an array, when you take off the front, you have to move everything down.
When we do this, when we do DQ, we do shift. Shift is a O of N operation because we have to move everything one spot to, depending on what we're looking at, to the left. Yeah. And that's a O of N operation. If we have a linked list, if you have 2 pointers, one in the front and one in the back, is really easy. It's constant time to add in the back, and it's constant time to remove from the front. The linked list. Yeah, later on we can go deeper into that. Cool. This one was tough. This one was tough. Thumbs down if you agree that this was tough. It's tough is down.
I started
Yeah.
doing something and
So, yes.
No, sorry.
So go. Yeah. So this one is asking specifically for you to find a bad commit in log n time. What do we know? I think we only know one thing, that's log n time. Binary search, right? We can do binary search on an array, right? But that array has to be sorted. You can't do binary search if you don't have a sorted array. And then that also we saw a binary search tree. A search on that tree will be also log n. So who could maybe summarize what the principle of binary search is? Yes, Lucas.
You're taking your array and you're finding the center of it, or as close to the center as you can. You ask if that's what you're looking for, and if it is greater than, or if it's smaller than, it's a sorted array, you're going to split. You're going to make 2 splits or 2 slices, like a before the middle and after the middle.
Okay.
Sort of, setup, and then depending on whether or not that center variable is larger or smaller, you grab the chunk of the array that you spliced in half, and ask the same question again. And you keep asking again and again until you find it.
Until you find the value, right? So that is like the dictionary. Like when you're looking for a word in the dictionary, let's say you're not as smart to figure out exactly where the letter J is, like you could sort of guess. But let's say as a computer, you're unable to guess that well, and then so you open the book in the middle and you check what letter you're currently on, and if the word you're looking for is on the letter part, then you just get rid of the first half, and then you just repeat the process on the later half. And you do that enough times, you'll find your answers. There's this visualization that I think I added to this. I think I added it to here, I'm not sure. Yeah. No, this is binary search article. Is this the one? No. I think I didn't add it here. If we do binary search visualization, there is this really good resource. I can send out the link later on. That it shows you this. It shows you this array. This is actually just one array. It's just that they wrap it in here. So this is index 0 to 15, and then here index 16, 17, and so on. So let's say in this array we're going to look for, let's say we're looking for 570. So we put here 570. And then linear search, we're familiar with that one. Linear search will be just iterate over the array, checking every single one. But that's linear time. Let's do binary search. And let's slow this a little bit down. Let me skip back. So the way in which it's going to do is we keep a pointer in the beginning, we keep a pointer in the end, and we put a pointer in the middle. So let's do binary search. So those are our 2 pointers. And then one in the beginning, one in the end, the other one in the middle. And that comparison, we did a comparison here, which was checking if our number is greater or less than 15. If it's less than 15, then it's going to repeat the step, but on the left side. In this case, is 570 is greater than 15. So it just sort of gets rid of the rest. We don't need to look at that because we know that a number is greater than. So then it moves the sort of front pointer to the middle plus 1, and then it repeats. Then we calculate the middle. We check this number. That's that green, that red. We're checking if the number we're looking for is greater than or less than this one. In this case, that is less. What happens is this pointer on the end is going to move here to the middle. And then we calculate the middle again, 570. That's the number we're looking for. And here, then, we found it, element found. So we needed to do the same on this one, but it's like hard because, well, these are not numbers, right? But this is sorted, right? In what way is it sorted? Well, it's actually sorted in 2 ways. Yes?
While the timestamp is like true, and it is slowly advancing over time, the array itself is like by index sorted. So you can kind of use that as a. So I was using the status versus the timestamp.
Right. Here the timestamp is actually like a sort of a distraction. We don't need to look at the timestamp. What we need to look at is that it's sorted in like the status. Like all the good ones come after or before, depending on how we're looking at, from the bad ones. And that is like how we sorted. So instead of numbers, we need to check. We're going to go to the middle. We're going to check if that's the bad commit. If that's not the bad commit, we know that the good commits are to the front of the array. So we don't want to move. So let's see how we can simplify this. First of all, also whenever you get a problem like this, that is like a huge input. This one is not as big, but it's still kind of hard to wrap our head around this. What you want to do is reduce it to a smaller size. A smaller, still a meaningful size. So I'm gonna remove a bunch of this. We're gonna need to put them back at some point because we wanted to test it on the end. So let's put something like this. I think this is 100 commits. Let me remove a good chunk from here. Also, let's remove a good chunk of the bad ones. Cool. So we have a smaller still representative input. So what we're going to do is we're going to go to the middle. Let's say from here, roughly, the middle is this one. Just roughly speaking. And we're going to check if this is okay, let's actually ask this question first. How do we know if it's the first bad commit? How do we know if it's the first bad commit? Cameron.
We're going to know that there's a good commit right before it.
There's a good commit right before it, right? So we know that this is the first bad commit, right? So there's one thing here where these timestamps, I think they are this timestamp should be actually flipped, since the bad commit was supposed to come after the good commits. We have a previous point where we know that it was good, and then after that, it went bad, right? But that doesn't really matter. As I said, that's rather a distraction. Okay, so we do know that the way in which we know that the first bad commit is because there is a good commit right after that. So this is the good commit. This is the first bad commit because the next one is good. So let's think of this as the input, this is the first commit, right? This is at index 0. In fact, you know what? Let's do this. Oops. We need to. Oops. Just forget about the timestamps. I guess I removed some commas. And we have this. Good and bad. We have our first one here. So what we're gonna do is we're gonna go to the middle here, and we're gonna check if it's good. If it's a good one, and we're looking for the first bad. Well, we want to check if it's a bad one and it's followed right next to it by a good one, right? This one is it a bad one? No. Is not. If it's not a bad one, don't even care. In this case, we know that this one is a good one. So when we're looking for the first bad one, in which direction do we have to move? To the right, right? Or down in this case, right? Because we know that then it's going to be on this side, right? So let's say we move on to the middle of that, which is, I might actually end up being on the first one, because then here we went to the middle of just that other half, and here we can check, is this a bad one? Yes, okay, let's check if the next thing after that is a good one. Then we would have found it. So that's just basically the approach. We go to the middle, we check if it's a bad one followed by a good one. If it is, then we found it, stop. If it's not, then if we landed on a good one, let's move to the right, because the bad ones are going to be to the right, and repeat the step. So in this case, then let's do that here. Now we're still gonna need a loop, but it's not gonna be a linear loop, or it's not gonna be a for loop. Right? But what kind of loop? Because we still want to keep repeating this step. Maybe even before we think of the loop, let's initialize 2 pointers. Let's do like front. We know that the front is 0, and let's do back. Commits length -1. Okay, so we got our 2 pointers at the 2 ends of the array. Then let's calculate the middle here. Let's call it mid. Let's do commits. Wait, what would the middle be? Commits length divided by 2. And we need to floor that, because in JavaScript we get decimal numbers, and we can't key into a decimal index, only integers. Okay, so we have our 3 pointers. I think we're gonna need to reevaluate this mid later on, but we got our mid. Then let's do. What do you think we have after this? Check. Maybe check if the one in the middle is followed by a good one. Let's do this. Let's check if the one in the middle. Let's do commits mid. If this one is, well, we want to check the status. So if this one is a bad commit, and the one right before it is a good commit, mid -1, that status, a good commit, then we will know that we found it. So in this case, let's return, now let's return just true. Let's return true if we found it, false if we didn't find it. Then later on we can worry about like this specific output. Okay. So we found it, then that's great. But how do we keep doing this? Because we need to check the middle, see if that one is the one we're looking for, which is a bad one right next to a good one. And if that's not the case, we want to keep, well, we want to check, do we move to the left or to the right? And we have to repeat that step. So we're going to need a while loop, right, to keep doing this. In fact, we need to perform this check in our while loop so that we don't have to hard code it and basically not have an algorithm. What would that while loop be? Let's think about what happens if we didn't find it. Let's say our algorithm works and it's going to do binary search. What happens when an element is not found? Yes.
If it's bad, we'd want to move left, but if it's good, we'd want to move right.
That's correct. But let's say going back to this example. Let's actually see it here. I'm going to put in a number that is not in the array, like let's say a number in the middle, maybe 600. 600 is not in this array. What is going to happen? What's going to be the result here? Let's check it out. Binary search. We're looking for 60. We start there. We go to the middle. We check, is this 600? No. Is 600 greater than? Then move to the right. Same to the middle. Is 600 greater than 271? No. Goes to the middle there. So anything that we see from this, from what happens when it was not found. We ended up with 3 circles. Well, we started with 3 circles, a green one, a blue one, and a yellow one. Where is the green one? Let's step back. Hey, can we step back? Can't step back. Oh yeah, step back. So here we have the 3 circles, right? The blue one in the beginning, the yellow one in the end. Let's play. Where's the play button? Anyone see the play button? Oh. Then here we're checking. Oh, I guess now I have to. Wait, this seems to be a bug in here. It broke. Right, like let's. We're looking for. Oh, but did we get a different set of numbers? 600. Binary search. Let's see if we can. Yeah, I can move it myself. So we check the middle. Is this 600? no, is it less than or greater than? If it's less than, let's move on to the left. Now this is our end, became that. Now our middle is the green one, so that one should go to the middle. And then we're checking if this is 600, which is the number 662. That's not 600. 600 is less than or greater than that, is going to be less, so we should check this side. Let's play. So that's, now we got our middle here. Now this is our front and this is our back. We got our middle there. Is this one 600? No. Do we have anywhere else to look? That one, that last one. We need to check that that one is, if that one is 600. In this case, we didn't find it. But where did the green circle end? So we got our mid. So our mid is there, then our high is there, as well as our low. But note here how the low surpassed the high. Right? Our low, which is supposed to be like what we call the front, surpassed our high here, our back in Oz. That's when we know then we need to stop. Once the 2 pointers reach the middle and that thing in the middle is not what we're looking for, then we need to stop there. So Michael, what is the conditional here?
Actually, for the model, I had basically, well, that condition right there in the if statement, I had that.
Okay.
And then I put the not.
But then does that work if it's not found? So in here, what we want to do is, as long as our front is less or equal to our back pointer, as long as they never cross each other, let's just keep doing this. We check if that commit is bad, and if the commit next to it is good, return true. Otherwise, then let's do else if the current commit. So actually, let's do here current commit. Let current commit equal commit at mid. So that can do this. Thinking we should have a previous commit. Let's call it previous commit, which is going to be equal to the one right before it, so that I don't have to type all this here. Just commit that status. And then here we're going to say else if the current commit status is bad, then we want to keep moving to the right. Is it to the right or to the left?
We gotta check both. That could be the first one.
If this is the first one, then we were going to catch it here. Because the first one, we know that is the first one bad because it's next to a good one. Right? So if it's bad and it's not next to a good one, so let's say we land here. So we want to go left, right? So we want our back pointer to go we want our back pointer, which let's say is here at the end, to go down to the middle, right? So then let's say if this is the case, then let's call back to become now our midpoint. And we should Should we recalculate the middle now? So let's do that one first, and let's do this rest. Else, since we know that there's just two status, bad or good, else we want the opposite, which is we want our front to go to our middle. Now we will need to recalculate our middle point because now it changed, right? Now we want the middle point between the back and front, no matter what those are. Neil.
Move the mid calculation to the while loop.
Move the mid calculation to the while loop. Yes, we're gonna need to move this one into the while loop. But then we also needed to work on a more general case rather than doing commit.length divided by 2, right? How could we do that? Back minus front. Back minus front. So our back starts at the length minus 1 minus the front. That'll give us the length on the first one, and then we divide that by 2. Does that still hold when we have
Should be
front plus back? Let's think about it. So if we have
You're getting the average.
So let's say
And that still works.
it will still work. So let's say we have this one, and we have an array of 1, 2, 3, 4, 5, 6, 7, 8. So we have our front, back, and mid. Front will be 0, back will be 7. In this case, our middle will be 7 divided by 2, 3.
It has to be the average because it's like the front is like 6 and the back is like 10. The average is like 7.5. And if you did that, it'd be 10 minus 6, which is 4, divided by 2, which is 2.
Can we still demonstrate that example with this input?
So for example, like 5 is the front and 7 is the back.
Right. So let's say we have 5 as the front, and then 7 is the back. Then what will be if we have this calculation? We have back minus front, which is 2 divided by 2. That gives us 1. Then our middle, so we have like F here and back here, right? And we try to keep going with this calculation about the middle being the back minus the front divided by 2. Then in here, when we do 7 minus 5, 2 divided by 2, then we get 1. And then 1 will not really be our middle point, right? We want our middle point to be 6. So then how do we fix that calculation there? Plus, yeah.
I'm sure to add the array that like
Not the array length, but we will need to do the plus. I mean?
Yeah, it's back plus, back plus front divided
Back plus front divided by 2.
by, yeah,
Getting the
5
average.
plus 7, 12 divided by 2, 6.
The average of the two is adding them all and dividing.
Instead of subtracting, okay. Cool. That's it. Because in the first try, then the back is 0 and the front is the length. So that works. And even in this case, I think the way that I initially solved it was actually a little bit less efficient, where I always add, I add, I add back the front, which I didn't realize that it's like not the idea that you're giving me about just adding the two and then subtracting. The way that I did it initially was I do this front minus back, and then I add front to the result. So if this one is 5, I just add the front, which is going to be 5, and then that gives me 5 plus 1, that gives me the middle.
That only works if you're going right.
Say that again?
That only works if you're going right.
Oh, that's a good point. Yeah, you're going left and right. So I guess my original solution for this is wrong. Cool, so let's try this. Anything else here? Do we?
Put return true.
Yeah, so that just, if it finds it, let's do that. Otherwise, let's return false. Let's try this out. Let's see if it finds it first. Node 5. Commit is not defined. Spelling mistakes. Yeah, I guess we need to do a console log here. So we found it. What happens if there is none? There is no bad commits. Oops, seems I stayed in an infinite loop.
Because you put equals front is less than
Oh. And then it never falls onto any of the other cases. Wait, really? Yeah, no. Any ideas here? Why is... Say that again? I'm updating back to the middle and front. Oh, I think +1, yeah. Let's see the way that it does it here. Yeah, when we update the back, we update it to skip back. We updated this one to leave out. Yeah, we updated not exactly the middle, but the middle +1, and the back -1. So the back comes the middle -1, and the front the middle +1. And it didn't find it there. Let's just double check here. I found it there. Then the last check will be with the original input, which I'm just going to bring back here. Let's see if it finds it first. Found it. Then let's return what we were asked for, which is an object with an index of mid and a commit with our actual current commit. Cool, we found it. Index 78, the first commit, that's bad. And we're doing binary search on our array of commits. The thing is, like, this one was tricky or confusing just because it's not using numbers, which is the general idea of, or which is the most commonly seen binary search. And it turns out that this is a real thing. Git lets you do binary search on your commits. There's a command called git bisect, where you can say, let's say yeah, this example is taken from there. If you in your code you have a bug and you want to find what was the commit that introduced that bug, you can call git bisect, and then start mark a sort of a front and a back commit. What Git does is it takes you to the middle of that, and then it asks you, is this a good commit or a bad commit? If you say it's a bad commit, then it moves left or right, depending on what you're looking for, and so on. Questions or comments on this one? This one is tricky. But this is, again, one of those things that are sort of expected of us, binary search, to be able to do. Cool, so we just have left the recursive sum, the BIGO, sorting algorithms, and printing the tree. From those, printing the tree, the recursive sum shouldn't take us long. The BIGO shouldn't take us long, as well as the print tree. The print tree was the one that's going to take us the longest. Let's take a 5-minute break and continue after that.
Pretty much mine is except for the back. So do you know how our Saturdays are gonna look?
Um,
Like stuck on weekdays or
um,
I need that shit.
to be honest, we don't have a set plan just yet defined. Most likely it's going to be half a day, some material, review or new, and then half the day working on your capstone. Because after, like, we have hackathon after this. Hackathon. Oh yeah, this is what it's gonna look like. This is gonna be either a new thing, but it's a new thing that is not. Well, we saw all the major things. Like, there's nothing that is going to be like super new in a way. Like, we're not gonna teach you another programming language. It's either gonna be like testing, like learning how to test your code with actually automated tests, reviewing DS&A. We cover like we
Is Ben still gonna come on Wednesdays?
yes.
Can you do it on Wednesdays?
Okay,
I don't like that.
that's fair. He definitely has a different style. He definitely has a different style.
Yeah.
You're supposed to try.
Cool. So, right. So we did the binary search. Let's go on to the recursive sum. I think I saw a few different interesting approaches. One constraint that we did say is like don't use global variables, right? Like don't have like because we could do like let total here equals 0, and then we could just have the recursion do the loop for us and add all the numbers. But what are some of the approaches that people went with? Yes, Douglas.
I actually avoided using any variable at all.
Okay.
By creating first with an if statement that is a capsule. Like that was the base case.
Okay.
Which is if the array.length equals 1, then you want to return array at 0.
Right. So let's think about that. Like we talked about, recursion always has to have 3 things: the base case, the recursive call, and it means to reach the base case at some point. It has to move towards the base case, and then the easiest way to start is thinking about the base case, thinking about what is the smallest input we can get. So then, Douglas, you were saying about your base case. What was your base case?
Since I'll be adding as I go along, the base case is if the array has a length of 1, then simply return array at 0.
Right. This is again, the smallest possible input. What's the smallest possible input we could get? An array of 1 element. And if we have to sum that, what's going to be the sum of the array of 1 element? Just the element itself. Okay, so we have a base case. Then after here, we're missing, should we, well, at this point we could do, well, should we care about the array being empty?
You just put dot array length, and then return, just return. Or return
Oh,
0.
okay. Yeah.
Return 0 instead of the array.
Like this. I guess we can explore with a few different cases.
Because if it's empty, then
Wait, I want to go with Douglas' approach first, and then we can see a different one. It will still be sort of similar, and we're going to sort of see it shaping. Yes. Right, the array length is equals to 1. Yes, thank you. Okay, cool. Then what do we do after here?
My else for that if was array.push array at 0 plus array at 1.
Oh, okay. array dot push, array 0. Oh, okay. And then you push plus 1?
Yeah, plus array. No, array 1 at index 1. And then I array shift twice. So array dot shift, array dot shift, and then recursive sum array.
Okay,
That way
so
I'm putting the sum at the end of the array, and getting rid of the 2 I just added. And then the next time it's called, it adds the next 2, sticks that sum at the end, gets rid of those 2 variables.
This is kind of clever. This is really clever. Let's see. So you do array dot shift because I was gonna say like, well, your array is growing, but the base case says for the first one, which you actually start removing stuff. Well, let's look at this one, and then you do a shift twice, right?
Right.
And then you just recurse.
Yeah, recursive sum with array.
With the same array.
Yeah.
Okay, so let's look at the array at 2 points. Let's look at it here. Console.log array. And let's look at it after here. Here, and I'm just gonna add a line so that we separate it. Let's put some quotes. Let's try this. This is yes, I would have never thought of this. This is cool. This is one of the funniest part of my job, just looking at your creativity when you code. So let's do node 6. Do we have a console log? No. So what Douglas is using here is like he's using the array itself to keep sort of an accumulator. So this is what he's doing. First he looks at the first 2 elements, right? And then, well, if the length is not 1, right? Then that means that we're going to execute the rest. If the length is 1, then we just return. So what he does is he adds the sum of the first element of the array and the second element of the array at the end of the array, and then we end up, this is our original array, then we add 5 plus 2, and then we add that to the end. He pushed to the end. And the next thing he does is he removes the 2 from the front with array shift, and then, we go back. This is this thing here. After shift 1, 5 went out. After shift again, 2 went out, and we were left with this. And the last element sort of is keeping track of sort of an accumulator, sort of. And then that just repeats. We have 9 and 11. That's 20. 20 gets added to the end, and then he unshifts, which takes these 2 out, and we end up with 7 and 2. And we end up with this. 7 and 20, that gets added to the end. The last one is 27. And now we get to, an array got to the level of just being 1 element. This is cool. Yes?
It's funny because I did kind of the same thing, but the opposite. And I thought it was kind of unique too.
Mm-hmm.
Like I just pop twice and add those 2 in a push. So basically,
Okay.
array dot push,
Mm-hmm.
array plus pop.
Got it.
So you're popping twice in the same line and also pushing it in the same line,
Mm-hmm.
and then you just return that array, or you put that array in the recursive and keep going to get nothing left.
Okay. Yeah, those are fine ways. I think the only reason why this will feel, even though it's a very creative solution, the only thing why I will sort of criticize it a little bit is just because it's modifying the input. You generally don't want your functions to modify what came in directly. You oftentimes just make a copy and then modify the copy and return the copy, and so on. Like,
I was going to ask, I did something similar, but I was going to ask if there's a way to do it without destroying the array.
Right. Yeah. So this wouldn't be a pure function. Let's just make sure, because I know that pure functions are functions that don't have side effects. The return value is only determined by its input values without observable side effects. Yeah, it doesn't say anything about modifying the inputs. I think other approaches. Describe yours, Michael.
Mine was the not length. Did you check if it's 0 or not?
So let's call it this. Yeah, I think this one has like a few different approaches. Let's see, maybe two more one after this. So you have, if there is no length.
Yeah, there returns 0.
So we could just do it like this.
Yeah.
Right? So if the array is empty, return 0. Okay, so that takes care of the array being empty. Right? If we pass in an empty array, just return 0 because there's nothing to sum. Okay?
And then return array.pop.
Return array.pop. So
Plus the recursion of the array.
plus the recursion of the array. So we do recursive sum array. Okay. This one should work in a similar, still should work. Let's try it out. The last one was 27. Ooh, we get call stack size exceeded. Oh, I forgot the return here. We got 27. Kathy, you have one similar to this one. Exactly the same? Yeah, cool.
If you want to make it pure, you just make a copy of the array, right?
Yeah.
The only thing about that is that, how would you
So let's look at this one. Let's look at the three parts. We got the base case. We got the recursive call. And let's think about the means in which it's going to reach the base case at some point. What are the means in which this one will reach the base case at some point? Michael.
array.pop means the last element.
Right. So we're making on every call, on every line 20, we make the array smaller. So remember that the base case are generally about bringing the input smaller until it reaches the base case. Recursion is generally about that. So in here we remove the first one, and we could have put it in a variable. We could have done like, I don't know, let num equal array pop, so that like that, and then we just say, okay, just return that num, the one that was popped at the end, plus the recursive call. We got 27. Let's see. What if we do? Let's do console log here. Console log num, and then also console log array. So we see what's going on. I always forget the log. So we got here. We pop the end of the array, which is 11, and then we are left with this. And we're literally saying, okay, the answer is going to be 11, the last element, plus whatever the rest is going to give us later, right? And then we got 11. This is the recursion, the way that I like to see it, or this is the recursion going up the stack, right? We're doing 11. Oh, actually, this would be a good case for maybe. Well, let's think about it yet. This is going to be 11 plus the sum of this stuff, and then we keep making the array smaller as we're popping. We pop 9, which is the next thing, and it's going to be 9 plus the sum of this. We don't know what the sum of this is yet, right? But the sum of this is going to be the sum of 2 plus that element, and the sum of one element is going to be that element plus the sum of the 0 of the empty array, and then the recursion starts to go. The call stack starts to go empty again. Like this is at the top of our stack, of our call stack. We got this call, and I was thinking that we could see it popping if we do something like result console. So let result equal this, and then we return result here. And then we could do console log result. And we should see the same thing where the console log goes sort of down and up again. Here, this is when we're summing, we're doing sum 5 plus the result of calling it with the empty array. The empty array is going to give us 0, so 5 plus 0, 5. Then we do, then that 5, that's the result of, 5 plus 0 is 0. 5 plus 0 is 5. And then that is the result of this, right? We know that that's the result of this. Then that 5 is used for the previous call, which was made with 2, and then that ends up being 2 plus 5, then we get 7. That 7 is the result of this, of calling the function with this. And then we get 7 plus 9, 16, and so on, and so forth. So the means in which, in this case, we are reaching our base case is by popping. That reduces our array, and we just recall recurse with that one. Note also here, yes. Sorry. Okay, let's look at that one next. So let's look at what happens if we console log here array at 1. What do you think is going to be? It's if we console log after a recursive call. So we do a recursive sum. We pass in this array. What is array at array 1 going to be at the end of a recursion? Empty or full? So thumbs up if it's empty. And thumb down if it's full. Cool, let's see. Empty. So well, this is sort of similar to the stack or the queue. Like we destroyed our array, cannot be used after that. Because when you do here, like this is also sort of important. When we pass this array here, we pass this array to our function. We're passing a reference. That's the right word. We're passing a reference to the array. And anything that touches that reference, that tries to modify that reference, is going to actually modify the original array. It's sort of also like a pointer. Sometimes people call it like a reference or a pointer. We're passing in a pointer to our array that's like literally a pointer that is pointing to the location in memory. If anything changes that location in memory, then it's modifying the array. Joey, your solution modifies the original array or doesn't? Okay, let's look at that one.
My base case is if array.length is less than or equal to 1, then return array index 0.
Okay, so are you doing the slice?
Yeah.
Okay, yes, that's the one. So your base case is if the array length is less than or equal to 1.
Less than.
Thank you.
Then return array at index 0.
Return the first element. Okay.
Then return array at index 0 plus the recursive sum function passing in the array slice 1.
So let's look at this one. Return one parenthesis. So we get our base case, which is when the length is 1. This could just be 1. Oh, but this has the problem where, well, if you pass in an empty array, it's going to return undefined, right? Because that is a slight problem, but it's not a big deal. we could just sort of check if it's empty, just return 0. If it's 1, length 1, return, let's actually do that. If the length is 0, return 0. If the length is 1, then return that first element.
Shouldn't it be return, just return? Because you're changing it from an array to a 0 number.
Well, I guess that depends on what is the sum of an empty array, right? It could be domain specific.
So you don't need the second line.
I don't need which one?
You don't need the second line. Does empty return 0?
Oh, otherwise just recurse. Yeah. We wouldn't need this one. Let's look at how this one was working. So let's see. We get still our answer 27, and we see that the array still has its elements. So we didn't modify the original array. The way in which this is not modifying the original array is because we do array slice. So we're basically adding the first element of the array plus the recursive call of the next elements in the array. And an array slice will create a copy of the array, slicing it, started at index 1, going up until the last index, the length. Yes?
I have a question. When creating a copy of the array, is that slice over and stuff?
That's correct. That will
You
be.
make a copy, because in the first one, I also made a copy. Like I did the spread operator as the first line. And instead of using array, I used a new array.
Okay.
But the thing is, doing the spread operator like dot slice or dot shift, all those things are like over and, right?
That's correct. Yeah.
That makes the recursive like over and squared.
That's correct. Yeah, so we'll make the recursive of n square. Because any of these operations, the slice or the shift we were doing is all of n. So it's better to add the numbers in an array with a regular for loop because that will be linear time. But this is sort of about demonstrating the point and understanding recursion, that efficiency. Another way will be, what if we, instead of passing the array, we just pass in the index? That will solve that problem. That's sort of like the other approach, but that will require us to pass in the array, an index, and an accumulator.
But we can create another function that recurses inside of that function.
Yes, William.
That's so similar to the way I did it. Is I passed the index, set to 0, and then passed the sum also, set to 0.
Let's do this one, yeah. Because I think this is also value on this one. And you could technically say that this function is pure because it's not modifying anything outside of it. You just pass in extra arguments. So, well, I didn't think we could find 4 different ways of doing this. So you have the recursive sum. What are your arguments?
The array, index, 0.
Oh, you start that one at 0?
Yeah.
Okay, I'm going to start it in when I call it. And then what's the next thing?
I just called sum.
Sum, okay. So we could also do this. And the way in which we're going to call it is, I'm going to call this one actually different. Just so that we don't break the other ones. Yes, so keep going.
For this, I have to, base case was if I is greater than or equal to array n plus 1.
Okay. So our base case here is I is going to keep increasing to at some point reach the array length, right? And once we reach the array length, what do we return? Okay, let's return 0. Okay, what else?
And then I just call a function recursively, and the way I was doing, I just sent the array, and I
Oh, you iterate over I here,
Yeah, I set I equal to 0 in the parameter.
but do you have like a for loop or a while loop?
I don't have.
Oh, okay. So then, what do you mean by iterate?
I just set I plus 1.
Right. We just increase I here.
And I set sum equal plus equal array I.
Mm-hmm. And this should give us the same result. Let's see if we.
2 plus 1 or base.
Oh, is this less than? Less than or equal to array length? Yeah. Wait, yeah.
2 plus 1 at the end.
Here?
Yeah.
Plus 1? This feels a little bit weird. While I is, it's because I didn't pass in here. So in here, then I pass my array. My index starts at 0, and my sum will start at 0. Right? My array I is 0. Sum at 0. No, like I think this base case feels weird. If I is greater than or equal to the array length, we got undefined. That's just because we forgot to call it here. Return recursive sum. We got 0. So we're going to increase I. So once I reaches the length, we just want to stop the recursion. Okay, so this is this case. Otherwise, recurse passing in. Let's actually do results equal sum plus or array at I plus sum. So we can just pass in here the new result. That becomes our new sum. We increased I, and it should work. Maybe I'm not looking good enough. Any extra eyeballs? Once it goes over it, oh, okay. No. You know what? So let's do console log here, I, as well as sum. Let's see how this is working. So we got 0, 5, 7, 16, 4, 27, 5, nan. Okay. And then 0. Dinesh? Sum plus the recursive call. Oh. That will be here. This is starting to.
It looks like it's just one side over the so if you do length -1.
Right. Let's not go. I shouldn't go to 5. Or if it goes to.
Because we return I plus 1 when you do the last one, recursion.
You result plus recursive.
So then you go into like the 6th index.
Wait, so we get that. Where did we get that now from? Adding what?
6th index, so but you're adding an extra index at the last recursion.
Okay, right. So if I is. Wait, I'm really confused now. Doing this equal to?
Yeah, equals to return 0. And then at 35, we want to return the result plus recursive.
But I think.
Result
Yeah, because we already have it here.
We know return.
Let's check this. Oh, now we're going 1 over it. If the length is, once we reach the end, let's return 0. We're using the sum as an accumulator.
Get rid of the result. The return is not plus.
Mm-hmm. And we get 0. We're getting deep into recursion. It returns 0 here, but we're never using, like, since we're never using, we're never using, wait, we have, this should return the sum here when that return the sum, right? When we reach the end, let's just return whatever ended up being accumulated in the sum. So the way in which this works is we see that on the first time we start at index I and sum 0. Then we do the length is not, the I is not equal to the length. If I is greater or equal to the length, let's see if this still works. Right, I is not greater or equal to the length. So then we go into the recursive part. We just calculate the result first before we pass it on to the next, which is adding the first element to the sum, which ends up being, let's also console log here. Let's console log I and the result. All right, so the third value is the result. This is on the first time, all of them are 0. Then index is 1, then the current element, or the sum is, wait, I meant to console log here, array at I, and then the sum. That's 5. Right. So we start our call with index 0. The first element is 5. Right? The index is not greater than the length. Then we calculate a result which is equal to the array at index I plus the sum, which is 5 plus 0. Then that becomes our new result. We hold on to it and we call it in here result. So that's 5. Now we call our recursive function again, passing the same array, but now increasing I. So now I is 1, right? Our current element is 2, and our accumulator of the sum is 5. Then we do 2 plus 5. That becomes our new accumulator, which comes into the next one when I is 2. Our current value is 9. Our current accumulator is 7, and so on until we reach 27, which is we reach through getting I to the end of the array. In that case, then we just return whatever we managed to accumulate in our sum. This one then is it's still recursion because it has all those cases. Our base case, it has our recursive call, and it also has a means to reach that base case at some point. Any final questions on these approaches for the recursive sum? From this, I think this is the one that I first came up with. Slicing it, adding the end, and then slicing it and sending that slice to the recursion. Comments or thoughts? Yeah.
What are the, what's like the performance of creating a function and calling it within that function?
What do you mean, like the performance? Like, it will still be measured in big O notation. The well,
Again, in the example that I gave you, you can make a copy,
mhm.
and then the actions, just define that as a function. Call that function a copy. That way it doesn't mess up the.
We could look at it after. The thing is that with recursion, we are using space because our stack is being filled up. So then this solution, even though like this one is O of n time, it's also O of n in space because we're using our call stack is being being filled with calls and as many calls as elements in the array in this case. Cool. Let's go on to the last one. Let's think about like the big O notation for this one. What were the answers given? Big O notation of this code for bar. Who says it's O of n? Who says it's O of n squared? O of n squared? For bar. I'm talking about bar. O of n squared. Okay, yes, that's the right answer. It's O of n squared. Why is it O of n squared? Malik.
Because the foo function is iterating through the entire array,
Uh-huh.
and the bar function calls the foo function at every index. So at every index is iterating through the entire array twice.
That's correct. That was a good explanation. For every element, bar is calling foo for every element of the array, and then foo is calling is iterating over the array again for every element in the array. This constitutes nested loops. And this is, even though we're doing it twice, this will be like this O of n squared plus O of n squared. And we're just adding them, we just disregard the second one. This is O of n squared. Cool. Matching the sorting algorithms. How did this one go? This is why I say like try to remember the keywords of the algorithms. So this one, bubble sort, right? How do you know it's bubble sort? Yes.
Because you're swapping two, or you're looking at two variables at a time, swapping them if one is larger than the other.
That's correct. That's the definition of bubble sort. What about this one? Merge sort. Why is merge sort? Right, because it splits in halves and then it merges at the end, literally merging. What about this one? Quick sort. Has a pivot. And what about this one? This one, insertion sort. This one, I think, like this one, you kind of get through it because of the previous ones. I'll say. On this one, yeah, like we're inserting at the end, depending, or we're inserting in the right position, and we have to shift the elements. Cool. Now this one was probably one of the hardest. Anybody got this one? Okay. Are those recursive solutions? Okay. Yours as well? Okay. Let's look at the recursive solution first. Just because it should be like 3 lines of code, right? Like 4 lines. So in a tree, there is no like trees are not a linear data structure, right? It's that you start here and you end here, like an array or a linked list or a stack or a queue. Those are linear data structures. But here is like you could say what's the start, but what is the end? Well, you could say there are 1, 2, 3, 4, 5, 6 ends, right? So how do we go on every single one and check that? So any initial ideas or discussion that we can make about traversing this tree? Cameron.
This reminded me when you were talking about too how the console logs stack up and then they release at the end. I kind of use it that way. I focus them on the left first, and then let the console logs stack up when I was going to the right. And then they all kind of just unfolded in the right order.
Okay. Michael.
If you break it down, there's like sub trees. So like if you take off the F, you have 2 trees, like B and J. But if you think about it like that, you keep doing that. The recursive order is like right, middle, left. I mean,
Well, you define that. You define the recursive order. So, but that's a good observation. Which trees are, or at least binary trees, are recursive by definition, because you have this tree, but if you focus only on this area, this is also a tree, and if you focus only on this area, this is also a tree, right? Same way, this is a tree, and this is a tree as well. So we can take that recursive definition for implementing a recursive function. So this was all about remembering that. I actually got this question for an apprenticeship. It was literally this question, like you have to print in alphabetical order. And here, the thing was to remember that the algorithms to traverse a tree, basically. There is depth first and breadth first. So there is algorithms that you could go deep first, or you can go wide first. And then in the ones that you go deep first, there are 3 classes that we breeze through with Ben, which is prefix. Sometimes they're known as suffix, infix, prefix, and the other words for those are in order, pre-order, and post-order. We can get to see them in the time we have. So if we think about this, like if we want to print this in alphabetical order, then that means that we have to get to A first, right? Like we start with F, we start with the root, so we can't do anything with the root, right? We need to sort of somehow get first to the A. Then once we know that there is nothing else to go, then just print that one, and the recursion somehow has to come back up somehow, and it has to print B, and then once they have visited A, which is the left, then visit the current node, then visit the right node. So I think let's just see it here. Cameron, do you want to share yours?
Sure. Like on slide?
No, like just tell me what I'm right here.
Yeah, so I don't know if anyone else did this, but I put if root left. Basically that is this.
Okay, but also let's think about the base cases, and we said base case will be generally we start with like the smallest input. So all we did is smallest case.
It's that last thing because I do recursive so differently than all these guys. I
but
just throw the recursive in there and put.
Does your one will work for like an empty? Like what happens if you get no null as a root? So let's say if there is nothing, if there is no root, if there is no node, let's just return. Otherwise, let's do console log. Console log the root, that value. Is it val or value? Val. Okay, so we're thinking the simplest case is when we don't have anything, and if we have something, let's just console log the value of that. Right? Now, then, once we have console log that, we have to recurse on the left and on the right. This is sort of the more mind-boggling part about the recursing on the left and on the right. So let's do the left first. So what we're gonna do is we're gonna call print tree, and we're gonna pass in this name is too long. I'm just gonna change it to print tree. then we do that left. Let's do this. We go on the left and then we go on the right. So here, if we go on with the tree that we have, this one. Say that again?
Line 55.
Where?
Line 55.
Oh, thank you. If we think of this, then the first time this function is called, we're going to console log f. Then once we console log f, we don't care. Let's just focus on this area of the the left tree. And imagine we've got rid of the rest, and now we have this smaller tree starting with the root on D. Then our recursion is going to console log D. Because we receive a root, and that's immediately what we call. Then after we console log D, we call our recursion on the left. And also note here that we're always going on the left first. Like when we call with F, we console log F, and right after that, we go to the left. So we call it with D. Let's actually also, well, we got it here. We already have it here, this console log. So let's look at what this result gives us. Note, this is print alphabetical. 9. Do I have F? F is the root node. Let's try this. So in here we get this order. We get F, D. So as the recursion is sort of coming down the tree, we get F, D, B, and A. Right, like that. So we get up until here. Now the recursion then tries to go to the left of A, but there is nothing there. In that case, it just returns, right? We have this return here. In that case, it just returns, but then it turns out that the function hadn't finished because we were executing on the left, but we also need to execute on the right. So once the first one on the left sort of finishes, then it's going to start on the right. Let's see how we can visualize this a little bit. Okay, let's look at this. So this is what is known as in-order traversal. This is in-order traversal because we are sort of visiting the nodes in that order. Wait, is this order? No, actually, I completely forgot. In-order traversal. Let's see. Tree traversal. Okay, no. So this is pre-order. In order is when we traverse the left subtree, then visit the root, and then traverse the right subtree. Right now, what we're doing is we're visiting the root by the console log. That's what it means. And then we recurse the left, and then we can recurse the right. So this is pre-order. Then if we do this is in order, because we visit the left tree first, and then we visit the root. And after that, we visit the right tree. And then if we put the console log here at the end, it ends up being post order, where we visit the tree on the left first, then the tree on the right, and finally the root. So these are literally the position in which we put this console log says what traversal it is. Now let's put this console log here in the middle for in-order traversal, and then we get our tree printed in alphabetical order. So the way in which this works is like this. Let's see if we get in-order traversal visualization. There's an animation here. enter key. Oh, but this one we'll need to insert the nodes. The way in which this works is, let's go back to our, where did I have that? Here. So if there's no root, we return. There is a root. What we do is we call our function on the left subtree. So then the function gets called with D. So let's look at, I'm not sure it does. Will be. Let's draw the stack here, and that'll be the end. This is the call stack. So on the first call, I'm just gonna call it p for print, our function. We call it with the root node, which is f. Right? I'm just gonna draw it like that. This is the root node. This is the first call we do. We call print with f, and then print with f is the root is not null. The root is left, and then what we do is we call our function again, but we call it with the left of f, which in this case then adds another thing to the stack, which is p with the root node d, right? And if we're looking at this d subtree, that's not null. Let's then add the left of d, which is b, so that we do print b, and this is what our stack is looking like. B is not null, we add to the stack, or internally is added to the stack, the call with P of adding now A. And then it turns out that A is not null, so we actually call P with null, which is the left of A, right? And at this point then it stops. Then it stops, and the recursion is starting to go back down or back up, depending on how you see it. So this one gets pops out because that just returned. Now, after that just returned, the current node we're at is A, right? Then we console log A. So once the call with the null value happen, then that just return, meaning the it's kind of hard to describe, but we sort of get back to where the previous one. So these functions are going deep into, because it's calling itself with a different value, but it's sort of going deeper. Once we're here, then our function, yeah, that'll be too long. We call it with the left of A, that return null, that finish. But our function P of A, as I'm calling now, P of A hasn't finished because P of A still has to, it had to recursion on the left side. It did that because it was null and just finished, but it hasn't finished. The console log is still yet to run, and the print tree on the right side is still yet to run. So we call, even though, so the recursion on the left finished, that was fine. Then the next thing was do the console log, so that console logs A. That console logs A on the first time. That console logs A, right? And P of A hasn't finished. Or after that, did it finish? Right, okay, after that it did finish because it console log A, and then it tries to call P with the right, which in this case is null. And then that one just finished. Once those two things, once A truly finished, P of A truly finished, because it returned, or all the statements were removed, then we get back here. Now, that one got popped off. Then the stack still has all this stuff to do. Now we go on B. It turns out that A part was the left recursion of B. So that one's done. After that, then console log, right, that line that I have highlighted, that was the part that just finished, that we just did. After that, then B gets printed, because that's that one, and then the B hasn't finished because it still has to go to the right. and then goes on to the right, pushing our calling our recursive call with the right of B, which is C. Then that goes here, and so on. So we get C, and then that will try to call C on the left side. That's no, we know that that's going to pop. It tries to also call P with the right of C. That's also going to pop. Before it popped that one, it console log C, and then we are back here. After that, we just did the recursion on the right side and on the left side of B. So B really finished now. We get that one gets out of the stack. Then we get back to D, and then it just repeats like that. We will just D will have finished the left side, right? We print it all on the left side. Then we print out D, and then the recursion on the right side starts, which is P of E. Then this one calls with the two nulls. We know that that's going to go anywhere. We do E, and so on. After we get to F, and after we finish with D, then that will finish the left recursion of that, and then it's going to start doing the same thing. Let's actually just do that last one. And here, once we printed D, E, then P of D really finished. Like all the statements were executed, so that one got added. And then all that stuff that we did was the recursion on the left side. Then we console log F, which is the current node, and then we put in J, which is the right side, and then we put in the left side of J, right? Because our recursion is going to the left first, which is going to be P of H, and then P of G. And this one calls with the two null, with the left is null, then we console log G. It tries to go recursion to the right. That one is null, it just returns, and this gets popped off. And so on. And then goes I, and so on. I hope that was a little bit helpful. And when you do this iteratively, the only difference is that you're implementing the stack yourself instead of using the internal one. We can look at that one later. Well, enjoy your day tomorrow.